Okay, that is time, so no more marking on your quizzes, please. We will go over the quiz in class, grade it like normal. I guess I'll go over the grading details here in a second. Before I do, though, I just want to say that also today we will be going over your next homework assignment after we're done with the quiz. And I designed these quiz problems specifically to be helping you with the next homework assignment and different types of error messages, problems that you might encounter on the next homework assignment. And so it's extra important to pay attention today about the grading and why things are the way they are, because you will encounter these situations again while you're actually coding. And they will be more difficult to identify while you're actually coding because they're not going to be sort of chopped up into nice logical chunks like this. They will be spread out through a horrible mixture of Python and SQL code at the same time. Okay, that said, we'll start here with problem one, and I will first walk through what problem one is, and then or the grading for it. Sorry, there we go. Missing my pen here for my tablet thing. We'll first walk through the answers, what the answers should be for problem one, and then after we do that, we'll talk about how the grading for it works. So on my right-hand side, we'll go through the same procedures like we've been doing. I'll do connect to pSQL in both the top right and the bottom right corners over here. Again, both connected to the same database, just two different sessions in the same database. And in the top right, that'll be my session one. I'll start with this create table T, a int primary key like this, semicolon, and hit enter. And again, please double check that I'm not making any typos as I'm going through here, because if I make typos, then that will obviously affect the final outcomes of what's going to happen. So again, when you see a primary key like this, then you should be thinking that that is a unique key that also has the not null constraint. There's no difference between primary keys and unique constraints combined with the not null constraint. So that's table T right here, line 2, timestamp 2, create table U, B, int references TA, semicolon, hit enter. Oh, I did have an error, up arrow. Back over here, change that R to an E, hit enter, and now we have two tables successfully created. Line 3, begin. My transaction in the top right. Line 4, something interesting happened. Begin isolation level repeatable read. Begin isolation level repeatable read. I don't think there's a typo, no, good. Line 6 up here. Insert into T, values, 9, semicolon, hit enter. All good. Now, line 7, the first thing where we might have to annotate something, we have a select statement. Again, for the select statements, I'm asking you to write what the final answer, what the output of that is going to be. So here we go, select count star from U, here, semicolon, hit enter. And we get 0 as the result because there is, in fact, nothing in U. There couldn't possibly be anything in U because we were inserting into T over here. But even if this insert into T over here was an insert into U, it wouldn't be a, it would not be, we would not see it because of the isolation properties of transactions. So getting my cursor, where's my writing thing? Sorry, where did my little button go? I don't know where my button went for writing stuff. Is that going to work? That is not going to work. Apologize for this. I will open up this file in a different way to do this better. there's that writing button. This one can go away to here. And so we're still, okay, apologize for the weirdness there. We're still on this problem 1. We just got up through line 7 here, running the select statement, and we had a 0. And so we should be writing a 0 next to that select statement. Line 8 in the top right corner up here is a commit, semicolon, hit enter. And then line 9 here is where we're going to have the most interesting thing going on. We have an insert into u values 9. Insert into u values 9, semicolon, and I'll hit enter in a second. But before I do that, we'll see that, okay, there is a 9 in T at this point. It's been committed. And so because of this references in table U, we need something in table T in order to be able to insert something into table U. And the question is, will this transaction on the right-hand side at line 9, will it see the value that's in table T over here? And so in the bottom right-hand corner, I will hit enter, and you see that we get an error message. So we should have an X through the 9 right here. We should have an X through that 9. And we get an error message because we are in the repeatable read isolation level, and that is means that as soon as we've made some sort of read from the database, so line 7 here, we've made a read from the database, we're guaranteed to be in a consistent state of the database, like the same state of the database everywhere else in this session. And so at timestamp 7, there was no value visible to this database, to this session, this transaction in the table T. And so that's why we're not able to do an insert here on line 9, because we're sort of at like the same version of the database between line 7 and 9. And then in the bottom right corner, if I were to say commit, then that's it says roll back because it doesn't actually commit anything because we had an error message, but there's nothing to annotate here. In terms of grading, so again, every problem worth 4 points. On all of these problems, you can get either 2 or 4 points or 0 points. If you got all of the annotations correct, so you said a 0 on line 7 and an X on line 9, then you get 4 out of the 4 points. To get full credit, you have to have every annotation correct, and you cannot have any extra annotations. In order to get 2 out of the 4 points, all you have to have is 1 annotation correct somewhere. So in this case, either a 0 on line 7 or an X on line 9. If you have either of those 2 things, then you get 2 out of the 4 points. If you do not have either of those 2 things, then you get 0 out of the 4 points. Any questions on why the problem is the way it is, or how the problem should be graded? Okay. Again, on your homework, you are going to be writing Python code that will be inserting into a database using different transactions, and understanding when those transactions are going to conflict or not conflict with each other will be very important. So this is the sort of thing that will be very important for your homework, understanding if you get an error that looks like this, why, what are some of the possible causes of this happening. Okay, on to problem number 2. And actually, so back up here on problem number 1. Problem number 1 was just basically copied from one of the notes somewhere. The only difference, I think, was I changed primary unique to primary key up there. Problem 2 is the only problem in this set that I created from scratch for the purposes of this quiz. All the other things are basically copied from the notes somewhere. So problem number 2, probably the hardest of them on this, this quiz. Okay, let's go through and run this. So we have 2 tables now that I have to drop in order to drop table U in order to make my database back into a clean state. Now we're ready to start problem 2. I will up here do a create table T, a int unique deferrable initially deferred. I always forget an R or add an F or something here, but I don't think there's a typo. I hit enter, it worked perfectly. And that was lines 1 through 4. Again, SQL doesn't care about white space, doesn't care about enters. You end a command with a semicolon, so the fact that I've typed it in all in one line is not semantically important. Line 5, we're going to begin isolation level read. This is uncommitted, like this, semicolon, and hit enter. Uh-oh, I need to have not a typo on. Oh dear. Did I also have a typo in the quiz? Is anybody seeing where my typo is? Uncommitted. Okay. And apparently on the quiz over here on the left-hand side, I only have one M. So we'll go through the answer as if it was typed in this way over here correctly. But because I made a mistake, I am a puny human making mistakes, everybody will get full credit on this problem in case that typo somehow affected how you were doing things. I guess technically there should have been an X through that command, and that would affect a lot of things downstream. So everybody will get 4 out of 4 on this problem, but we'll still go through it because it'll be important for your homework. I apologize sincerely for that problem. Okay, so that is lines 1 through 6 that we have done now. Line 7 is where we are. Insert into T values 5. Insert into T values 5, semicolon, hit enter. This is in, this, by the way, is in the read uncommitted transaction isolation level. In Postgres, read uncommitted behaves exactly the same way as read committed. They are allowed to behave differently. They are allowed to have what are called dirty reads, where there is no isolation at all between transactions when you are in the read uncommitted isolation level. In Postgres, though, those dirty reads can never happen under any circumstance, and this read uncommitted is exactly the same as the default isolation level of read committed. And so without my typo, line 5 to 6 over here is the exact same thing as just a begin command. So there's nothing special going on actually about this transaction. So line 7, I've now inserted my value 5 here. Line 8, starting a new transaction over here in the bottom right corner, session 2, begin, and we'll do a select count star from T, semicolon, hit enter. That should have a 0 over here. As my result from that select. Line 10, insert into T value 6, insert into T values 6, semicolon, like this. And there's no possibility of us blocking here because the 5 and the 6 are different values. Anytime you have a unique constraint in general, the unique constraints from a performance runtime perspective are a little bit scary because they can cause things to block or deadlock. But in this case, we are not having that as a situation. That was line 10. We're now on line 11. Insert into T value 6 in the top right corner over here. Insert into T values 6 like this, semicolon, and I'll hit enter here in a second. But now we have a situation where we are inserting into the table up here, this value 6, and we don't know whether we're going to be able or not do it because the 6 over here is the same value. In this case, though, on the top right corner, when I hit enter, you'll notice that we are not blocking because on line 3, when I defined this unique constraint, I defined it as deferrable initially deferred. One of the advantages of this deferrable initially deferred property up here on unique constraints is that you're not going to block as often, much less likely to run into deadlocks. And so this line 3 up here is a common thing to add for performance reasons to SQL databases when you have unique constraints. This is one of the things, again, you're in your database that you'll be working with for your homework. You'll have a lot of unique constraints, and you'll have to think about ways of dealing with this. And these these deferrable constraints are a good tool for dealing with this. So there's no blocking going on here on line 11 because of that deferring. Line 12, select count star from T, do up arrow, and hit enter over here. Because of the isolation between these two transactions, we only see one row that's been inserted on line 12 from line 10 over here. We don't see the 7 and the 11 that's been inserted. So line 12, that should have a 1 in our output from that select statement right here. We now have another insert statement, insert into T values 5, insert into T values 5 like this, semicolon, hit enter. And again, there's no blocking going on, even though there's a 5 over here, a 5 over here. Same values being inserted. There is no blocking going on because we have a deferrable constraint, and so we are not checking whether this constraint will be satisfied until we end the transactions. If I did not have line 3, at this point we would have a deadlock, and one of these transactions would get aborted by Postgres, and we would have to retry that transaction from scratch. But because we're deferring that constraint, we don't have the deadlock, and we get the better performance. Line 14 now, the transaction on the right-hand side, we're going to abort that transaction. Abort, semicolon, hit enter, and that's totally okay. It means that this 6 and this 5 will not get added to the database, so there's no way they can compete with this 5 and this 6 over here. And so on line 15, when I do a commit up here, commit, semicolon, hit enter, then there are no problems. That does not error. Line 16 now, select count star from T, select count star from T. Even though the transaction on the right-hand side was aborted, those two values not inserted, this line 16 select count star is able to see the values from line 7 and 11 because they've been committed before line 16. And so we still have a 2 over here for line 16. 0, 1, 2 as the what I was intending to be the correct answer. Technically, though, because of my typo, there should be an X over here, which would affect a bunch of things. And so everybody gets 4 out of 4 points on the problem, no matter what you put. And again, I apologize for such a horrible mistake. Any questions, though, on what, maybe before I pause for questions, how is this going to be important on your homework assignment? Again, on your homework assignment, you will be having unique constraints. If you do not have the deferrable, initially deferred line on those constraints, then you are very likely to run into deadlock situations or performance situations involving sessions, transactions being blocked, waiting for other transactions. One of the tools that we have to reduce those performance problems is deferring those constraints until the commit line. So this isn't going to solve everything, but it is a good tool for solving many things, and in this case, prevented a deadlock. Any questions about this problem? Then problem number 3. Okay, let's drop our previous tables. Drop table T. I don't think there was a table U, but I'll run the command anyways. We're not in a transaction anywhere, so we're ready to start problem 3 over here. Problem 3, copied and pasted from one of your notes packets. So create table T, A, int, semicolon, insert into T values 9, semicolon, up arrow, change that to 10. That's lines 1 through 3. We're now ready to begin the transaction with a begin, semicolon over here. Line 5 and 6 in the bottom right corner, session 2, begin isolation level, repeatable read. No typos, yes. That's now we're in transactions in both of them, ready to start updating and deleting things. Line 7, update T set A equals A plus 1. Update, we'll go ahead and get our capitalization consistent, although it doesn't matter. Update T set A equals A plus 1, semicolon, hit enter. How is this going to appear in your homework? Well, you're going to be in your homework having to update, not just insert into the database, but update certain rows. And you'll need to be able to understand how, if multiple transactions are updating multiple rows at the same time, what is going to happen in those different transactions in weird edge cases like the one we're about to see. So we've just run line 7 here, updating this row that's not committed yet. And so because it's not committed, it's definitely not visible to the transaction over here on the right-hand side. Line 8, we'll write delete from T where A equals 10, semicolon, hit enter. And at this point, we get a block on line 8. Why do we get a block? Because there's no table level locks that are conflicting between line 8 and line 7. The table level locks are allowed to proceed here, but the row level locks are going to conflict between line 7 and line 8, and so that's why line 8 is going to block. Recall again that the delete command up here, you can think of it as being divided up into 2 steps. The first step is a select, and the second step is actually performing the delete. And so right now on line 8, we've sort of run a select statement to find what are the rows that match this query, this condition over here, A equals 10. And it's only this second row over here that's going to match that value over here. So line 3, The row inserted on line 3 is the thing that we've selected, and we're waiting on to see whether it's going to be updated or not. But we don't care about what's going to happen to line 2 up here because that did not match our condition. We are not waiting on the row with 9. We're only waiting on the row with 10. Line 9 in the top right corner, a commit, semicolon, hit enter. And at this point on the top right corner, that happened perfectly okay. No errors in the top right corner, no errors on line 9, but line 8 did in fact cause an error because of our repeatable read isolation level. When we do this delete from t where a equals 10, this the very first time and through that select statement, we had a different value over here of 10 in the row. Line 3 originally at 10. When we first saw the row, it was a 10 over here in that like initial hidden select statement. But then the update changed that row to be an 11. We committed that, and now there's no possible way for Postgres to use a repeatable read isolation level to have the initial select and the delete see the same value. And so we get this error message about not being able to serialize access. This phrase serialize access means that basically what I just said, that the two select statements happening in that delete internally that we can't see are not, there's no physically possible way for them to get the same values, and so we have to get an error because we're in the repeatable read isolation level. So we should have a circle here for blocking and an X here for erroring. Line 10, then the commit down here, again, not going to do anything, just rolling back the transaction. For full credit on this problem, you have to have on line 8 the circle and the X and no other annotations anywhere else. If you have at least one of those annotations, but not both, or you have something written somewhere else, then you get 2 out of the 4 points. If you have neither a circle nor an X on line 8, then you get 0 out of the 4 points. Any questions on problem 3 right here? Then problem 4, a nice long one, but also copied and pasted from somewhere. So you've seen this before if you work through all the notes packets. I will drop my table T. I don't think there's a table U, but let's run that anyways. We're not in a transaction in either way, so we're ready to start problem number 4. Create table T, a int primary key, semicolon, created the table. Line 2, we'll do it over here in the bottom right corner. Create table U, B int references T of A, deferrable initially deferred. No errors, excellent. Line 6, ready to start the interesting things. Begin our transactions. Insert into T values 1, semicolon, up arrow, insert into T values 2, up arrow. Now it's not inserting into T, but inserting into U values 2. There's no problem here because there is already a value in T over here that corresponds to the value that we inserted on line 9 right here. So that can't possibly throw an error. But even if it did not satisfy the foreign key constraint up here, because we are deferring that foreign key constraint until committing, this line 9 cannot possibly throw an error no matter what the value is over here. Line 10, begin isolation level, repeatable read. Begin isolation level, repeatable read. Semicolon, hit enter. And now line 12, insert into U values 3. Insert into U values 3, semicolon. And this does not satisfy our foreign key constraint, does not satisfy this references up here because there is no 3 value in the U table. But because we are deferring that check until the committing of the transaction, this does not throw an error. So there's nothing to annotate on line 12 here. Line 13, select count star from T in the top right corner. Select count star from T, semicolon. And at this point, we have 2 things in our table up here. And so put a 2 right there. Line 14, insert into U values 1. Insert into U values 1. Also something that we're not going to check that foreign key constraint yet because of it being deferred. Line 15, insert into t values 3. Insert into t values 3, semicolon, hit enter. And now that we've done that insertion over here on line 15, it'll be okay that line 12 over here inserted the 3 into u. We will, in the future, satisfy this foreign key constraint when we decide to check it. So that was line 15. We're now on line 16. Let's commit this transaction up here. We now have access to all that information. Line 17, update u set b equals to 5. Line 17, this is on session 2, bottom right corner, update u set b equals to 5, semicolon, hit enter. This is going to cause many things to potentially break because this b equals 5. Now our 5 up here is going to reference things that are not in our table T over here. Nowhere did we insert into T values 5. But all of our contents inside of U are going to be set equal to 5 now. Whenever you have an update or a delete without a where clause, it means that it'll apply that condition to everything. So everything will now have b equal to 5. In the bottom right corner now, that was line 17. I'm running line 18, commit, semicolon, hit enter. And we now finally get our error message over here about the constraint not being valid, not being satisfied, because on line 17 over here, when we do b equals 5, and there is no 5 in table T, that is the cause of our failed constraints. And so 18 over here should have an X through it because that line erred. And again, 17 is the key line that caused that one to error. Still have some select statements to run though. So line 19, bottom right corner, select count star from T, semicolon, hit enter. We have 3 things inside of the T table because even though on the right-hand side this transaction failed, on the left-hand side that transaction happened without any problems. And so everything was, in fact, inserted just fine into the T table. And again, it doesn't matter which session that you run that select from, whether it's the right-hand side or the left-hand side, whether it's the top or the bottom over here, they'll both have access to the same information at this point, not inside of any transactions. So I'll run the same exact command again for line 20, select count star from T, semicolon, hit enter, and also get the value of 3 down here. In order to get full credit on this problem, you have to have all 4 of these annotations, a 2 up here, a 3 down here, an X, and a 3, and you cannot have any other additional annotations anywhere else. So that's a full credit answer right there. If you have any other additional annotations or you are missing any of these annotations right here, as long as you got one of them correct, you get 2 out of the 4 points. If you got none of them correct, then you get 0 out of the 4 points. Any questions on this problem? Yes, Sabizu. So the question is, if line 17 over here did not exist without this update statement, would we still get an error? And in this case, on lines 10 through 11 over here, we have the begin isolation level repeatable read. And so what this means is that throughout this transaction over here, we're going to be locked into the state of as if the database is at the state that it is when we run our first command. So line 12 over here, when we run our first command over here, this insert into U values 3. At this point in time, at line 12, there is nothing inside of the T table. And so this is going to not be able to be satisfied at line 12. We would still be performing the constraint check on the commit at line 18 down here, but because it's a repeatable read isolation level, we would not then have access to new information that was inserted inside of other rows over here. So the question was, if you remove line 17, you still get an error why? And the answer, short answer, is because of the repeatable read isolation level up here. But with the update down here, it doesn't matter what type of isolation level we're using, we're going to get an error on line 18. Good question. Any other questions? Oh, yes.
I guess my question is, for like line 17, since whenever people read, like in the row that it's like blocking, or like one of the rows it's blocking has changed since the transaction began. So wouldn't that cause an error on something?
So question is here on line 17. This is updating every row inside of U because there is no where clause. So it's updating every row inside of U. And we've updated 2 rows inside of U before here on line 12 and 14. And the question is, so why is this not causing an error about there's nothing to update or something along those lines? And the answer is because all of the changes here to U are happening inside of this same transaction. And so repeatable read doesn't mean that the database, like the values are always guaranteed to be exactly the same. It means that something outside of the transaction cannot possibly change them. But here, these insert values, these are still allowed to modify the rows inside of our table. And if we had other updates, deletes, whatever, those would be perfectly allowed. It's just that these things over here, these commands on the left-hand side in a different session could not interfere with this transaction on the right-hand side. In this case, the only thing on the left-hand side that modifies, talks about table U in any way is line 9 over here. And line 9 inserting into the U happens before the beginning of our transaction on the right-hand side. And so that doesn't interfere with the isolation level things. Yes?
Like, line 9 happens before the...
Oh, I'm sorry. Yes, that's a good point. Line 9 over here, this does in fact happen before, but it doesn't take effect because of this commit. So I misspoke before. This transaction over here does not see this row over here, does not see this row because it was not committed before the transaction happened. But I guess that still doesn't affect anything. There's still no error over here. It just means that if this update command were to happen successfully, it would not have affected this row over here. The condition over here would not have matched this over here, and so it would not have updated this value. But it doesn't cause an error in any way. Yeah, I guess, so that it's a good question, definitely going into the weeds of things here, definitely the sort of question you want to be asking. If you still have questions about that sort of thing, any of the details of any of these problems, happy to address them in whatever gory level of detail you would like after class. But for now, we'll be done with the quiz. Make sure you've totaled up your points. And every time in the last 3 or 4 quizzes, there's been 1 or 2 students who have not written your names on the quizzes. So please double check that you have your name on the quiz before passing it up, and pass it up to me. Let's see this. I'm going to pile here. Wait, any other quizzes that I need to get? Okay, today, or the remainder of our class today, we're starting a new topic over here. This topic 8 of SQL and Python. The idea is how to modify the database effectively. We sort of started talking about that on your last lab, but we will be getting into more significant details about it. Really digging into the performance implications of all the different things that we've seen so far. Some quick announcements. No lab tomorrow because of Cesar Chavez Day, so hope you all enjoy a good day off. And then I want to do a quick outline of the rest of the semester to see how our assignment that we'll be talking about today fits into everything else that we'll be doing through the end of the semester. and then we'll talk about the assignment here. So the highlight here is that you'll have 3 more homework assignments in this class, 3 more programming projects. This is, again, for all students. Everybody will have 3 more homeworks, and the basic idea is that we're going to take the Twitter analysis that we did previously using the shell and the MapReduce, and we're going to now do that inside of Postgres. The highlights of what we'll see is that, so you might not have previously found that the shell plus MapReduce was easy to code, so I have easy in scare quotes over here. But many things about that are much easier than the things that we will be seeing now, especially because of these locks and transaction issues and just getting the data into the database. There'll be a lot of challenges with that. So you'll see that this MapReduce style coding, probably most of you will think about as being a lot easier than the things we're going to do next. The highlight of the MapReduce, why did we do it? It was faster than the non-parallel code. We could get basically as much speed up as we wanted based on how many cores that we had. But really, it was still slow overall. That maybe if you had best case scenario, full Lambda server to yourself, it took you I don't know, 3 or 4 hours to have all your code run. Could be a couple days if your code was slow for whatever reason, or other people were using the Lambda server. And if we're developing a web page, for example, a couple hours to return a query is not good enough for us. So now what we're going to do is we're going to be using Postgres to do all of this analysis. We'll see that you can run queries in milliseconds instead of hours, so much, much faster, fast enough to have real-time response in web pages. And what we'll see is that the hard part about doing that is actually getting the data into Postgres. Once you have the data into Postgres, writing SQL queries that will be fast will be fairly easy. And again, easy in scare quotes maybe, but definitely easier than getting the stuff into Postgres. The hard part here is just going to be getting the data into Postgres. But once we've done that, then running these queries in milliseconds will be, again, much easier. Due dates here, the next 3 assignments, basically 1 a week. I think if you're looking at the webpage right now, you'll see that this is actually crossed out. I've changed this, so instead of next Tuesday, next Thursday is when your next homework assignment will be due, so you have a full week to work on it. But the other ones still due on Tuesdays after that. And again, the idea of these 3 homework assignments here, you'll start off this week just inserting the data correctly, then inserting the data faster, and then finally, the last assignment here, querying the data fast, getting the answers out in milliseconds. You'll still have some labs and quizzes. Then the last part here, how things will break down differently for graduating students versus non-graduating students. You'll have the graduating students, you'll have your final exams the week of 22 to 26 April. There'll be one-on-one oral exams. I know a handful of you have asked me about what that's going to look like so far. Starting next week, we'll talk about exactly what will be on those and how to prepare for those. But if you would like to just get your time slots set up, you can do that over here. Expect them to be like an hour in length and approximately 20% of your final grade. Non-graduating students, you'll have one more additional coding project, and you'll still have this oral exam. It'll just be later during finals week. Any questions about anything administrative? Okay, probably lots of questions about the final exam, especially what the details of what that's going to look like. Again, we'll cover that coming up here in the coming weeks. But for now, I want us to make sure we have enough time today to talk about your programming assignment. So it's been posted now, again, under this topic 8 folder in this homework Twitter Postgres submodule. And so we're going to move over there in order to take a look at your assignment. There it is over here. Twitter Postgres. You'll notice that there are 2 badges up here instead of 1 this time. So the grading wise, this assignment is worth 16 points, and each one of these badges are going to be worth 8 points apiece. This normalized one over here is, this denormalized badge we'll see is going to be much easier to get running correctly. So I'd recommend starting with this one. And then this normalized one is going to be much harder to get running correctly. And so we'll talk next about the differences, what you have to do with those, and why that's the case. Otherwise, the format of this, the instructions, same as what you've seen previously. The tasks listed in detail down here. And so we'll go through about the differences between these two badges next. I'm going to switch to a terminal in order to do that. So I have a terminal opened over here into this same repository. And the structure of this repository is the same overall structure as your Pagilla repository homework structures. That you still have this SQL folder over here, ls SQL like this. There's a bunch of problems in there. You have this expected folder, which has the expected output for those problems. And this run tests that's going to run the SQL and check to see if it matches the expected output. In this case, though, I'm actually giving you all of the SQL queries. So if we take for a second, I'll vim SQL slash simple/01.sql. I'm actually giving you the SQL query right here, what it's supposed to be, and I'm giving you the expected output. Vim expected/simple01.out. There's the expected output of just shy of 10,000 rows in this table. Why am I doing that? It's because you're not going to write any SQL for this problem. Instead of this assignment being about writing SQL queries that are correct, it's about getting the correct data into the database. And if you do get the correct data into the database, then these SQL queries will run correctly. So there's two files over here, loadtweets.py, loadtweets.sh, that you'll have to write. These are the files responsible for loading those tweets into the database. And if you write these files correctly, then the SQL tests over here will pass. If you do not write them correctly, then they will fail. So these are the files that you'll be modifying. Inside, let's take a look at the Docker Compose here for a second. Vim docker compose.yaml. You'll see that there are two services now instead of just one, this PG denormalized and this PG normalized service. So there'll be two different versions of the database that you'll have to be working with. We'll go over what those differences are here in a second. It's an important thing to take away from this assignment is that there'll be two different databases, and you'll see two different techniques for, sometimes we call it marshalling data from one source into another. So marshalling data into these databases that are designed differently. Also notice that these databases, unlike your previous assignments, are using volumes here. So this is different than the Pagilla assignment. Pagilla did not have volumes. These databases do have volumes. And recall that the volume is used to make our data persistent, so it does not leave when the containers are brought down. And so you will have to, as you are debugging things, if you've ever inserted the wrong data into the databases, not only will you have to bring the volumes down, but you'll have to actually delete those volumes. If I come back over here for a second, there's a big hint on that down here. That's what this hint is saying, is that if you run into problems where your database is corrupted somehow because you've most likely inserted incorrect data, then you can't just run Docker Compose down. You have to run all these other steps as well. Okay, so now what's the difference between this denormalized and this normalized database? Again, the denormalized is going to be the one that is easier to use, so we'll start talking about that, and then we'll go over the normalized database after the denormalized database. Inside of my repository here, there's again this services folder, ls services, and I'll do an ls-R with the recursive so we can see the contents of all of it at once. Both of these normalized and denormalized databases just have a Docker file and a schema.sql file inside of them. And the only difference between these two databases, the only difference is how they are storing the data, how that data is structured in this schema.sql file. So let's take a look at the denormalized one first, schema.sql. Vim services /pg underscore denormalized /schema.sql and open that up. This line 1 up here, this set on air stop on, Not super important, but it's just saying that if there is an error somewhere in this file, then the database will stop doing whatever it's doing and not continue. You're not going to have to modify this file at all, so there's no way that that'll impact you. It's just a common thing to do when you're designing the schema for databases, so that you either know that everything is perfect or everything does not exist. You also see that all of this is inside of a transaction here. So either all of these tables get created or none of them gets created. You'll never be in like a weird situation where only certain tables are created and other ones aren't. The important thing about this denormalized version of the database, again, a denormalized database, there was these many different normal forms that we said we're not going to talk about because only database nerds care about that and real world people don't care about that at all. What real world people care about is there's this sort of spectrum between normalization and denormalization. And on this spectrum, denormalized means that things have been combined together somehow, and normalized means that things have been broken apart somehow. So in the denormalized database, things have been combined together in the maximum possible way, and every tweet is going to be stored as just an individual line inside of this table right here. This tweets underscore JSONB table is going to store all of the tweets in our database. In this case, the JSONB type, so this is the name of the column, this is the type of the column. The JSONB type is what we'll be using to store this data. One of the nice things about Postgres is that it has excellent support for JSON data inside of it. It was the first relational database to have this support for JSON. And other databases like MySQL or SQLite or even Oracle still don't have this like good JSON support like Postgres does. They're sort of catching up, trying to catch up, but Postgres is basically anything you might possibly want to do with JSON, it's able to do it well. And this is the only table that you'll really have to consider over here for our for this database. There's a bunch of views that have been defined based on this table. You don't need to necessarily fully understand these views, though. The purpose of these views is so that if I open up, for example, my simple01.sql file again in another tab, this file over here is referencing this tweets relation, not the tweets underscore JSONB relation. And these views down here are somehow extracting information from this table up here, putting it into a different form that's suitable for these SQL queries. So they're here for your reference if you would like to see them, but you're not going to be required to work with them. It's really just this tweets underscore JSONB table that's important. In order to get the data into this tweets underscore JSONB table, what you'll have to do is I'm going to go back over to our topic 8 folder now, and there is a line down here about the copy command. This incantation right here is how you can upload things straight from a JSON file into a database. And so you'll just have to modify this incantation to do that uploading and get the data in here. Where do you put that? Inside of this loadtweets.sh file. The loadtweets.sh file is the file responsible for loading things into the database. Up here in this files variable, we'll list all the files that will contain our data that we'll be loading up, and then we'll load the data into the two different databases here. And so you'll just have to write a one-line command right here that's from this incantation, modifying things just a little bit so that it works with the structure of your database, but it's just a one-line change right here to get the denormalized thing working. And after you do that, you get half the points on the problem. This, I guess, documentation for this incantation right here is this reference right here. It's where it comes from. And so if you need to understand what's going on here, read that first and then work through what you need to change here. It's a super fast, high-level thing, but any questions about what you need to do for the denormalized database at a high level? Okay, so just again, summary, one line change right here will make all the test cases pass for the denormalized database. At this point, this test-data.zip file, so one of the nice things about Vim is you can open up zip files directly, and we can see the contents of here directly. It only has just shy of 10,000 lines inside of it. So it's a very small file, and so speed is not going to be important for this first assignment here. The only thing that will be important is correctness, and then after this assignment, we'll go on to making it fast using the actual like full data set instead of this small subsample of the data sets. So we talked about another trade-off between the denormalized and the normalized databases. The denormalized databases often much, much faster than the normalized databases, and you will see that in this assignment right here. The denormalized database, so notice coming back over to the schema, there are no like foreign key constraints, there are no unique constraints, nothing like that inside of this schema. And so the database, while it's inserting the data, does not have anything that it has to check about correctness as it's doing things. And so the copy command will go very, very fast and very easy to implement. The normalized database, though, is going to be both much slower and much harder to implement because of additional constraints that it's going to have. So I'm now going to close out of all of these files, :QA, and we'll take a look at the normalized database. So Vim services/pg_normalized/schema.sql. And now inside of this normalized database, you can see that there are going to be many, many different tables down here, many different tables that you'll have to insert data into instead of just one table. So that should strike you as it's obviously more complicated because there are more things, more moving parts going on here. And if you look at these tables, you'll see a lot of things like foreign key constraints inside of here, or there'll be primary keys. So again, primary key being a unique constraint. And so there'll be a lot of potential for things like blocking and deadlocking going on if you're not inserting things in the right way. Fortunately, I've provided you I think a pretty good outline of what your code should look like to do that inserting. It's in this load_tweets.py file. And to insert the data into the normalized database, you'll have to make changes to this load_tweets.py file. So let's go vim load_tweets.py. There's a handful of helper functions at the top of this file. This remove nulls function is something that gets called later. This get ID URLs function, also something called later. You don't have to make any changes to these two functions up here. Instead, you're going to be modifying this insert tweet function. This insert tweet function takes a database connection and a single line of JSON, which I've called this tweet variable, and it will parse through that tweet variable, adding all the appropriate information to the appropriate tables and columns. I'll go through that file here, that function here in a second, but before I do that, I'm going to press Shift-G to take myself to the bottom of this file, and down here in this, so in Python, if you have a script, it's customary to put it inside an if statement right here, this if name equals main, and now this will only get called when this file is called as a script. And what this code down here is doing is it's going to actually connect to the database, loop through whatever the input files are, extract your tweets down here, and pass them to the insert tweet function. You don't have to make any modifications to this portion of the code down here. The only place where you'll have to make modifications is to the insert tweet function itself. Currently, the code is correctly getting all of the tweets, putting it in, passing them to this function, and you just have to do the right thing with each of those tweets. Okay, so let's find out what is that insert tweet function doing and what are you supposed to do for it. So again, two arguments up here, this connection argument and this tweet argument right here. The tweet argument is the JSON dictionary or the JSON structure containing all the information about that tweet. And you'll have to extract that information and run the appropriate insert commands into the database. The anywhere where you will have to do an insert command. I've already provided you an outline, something like this, where it says SQL, the variable equals this text thing, and then you put your SQL query, whatever it is, like an insert statement or an update statement, into this into the text right here. The structure of that will be exactly the same as from your lab about how you inserted things into the lab, so you can reference that for how to do that. You'll put the appropriate insert code right here and then just call the appropriate function to run that SQL query. There are many different spots like that. And so there's, I don't know, a dozen or so insert commands that you'll have to be running in order to do that. If at any point there's like some sort of information that you have to extract from the tweet and it's complex, like a complicated extraction process, then I've already done the extraction process for you and stored that information in a variable somewhere. So for example, the text variable has a little bit of complicated extraction going on here. This geo coordinates have a lot of complicated extraction going on here. You don't have to modify any of that code. You can just use the results that I'm getting down here and pass those into the appropriate SQL command down here in order to insert that into the database. As you're doing this, again, you're likely to get many constraint violation errors, blocking errors, things like that. And so hopefully your understanding of things that we were practicing with the quiz will help you understand whatever sort of weird error messages you're getting as you're filling out the commands down here. Any questions about, yes, Abizar? Yeah, so this is a great question. The question is, like, how do I go about approaching a problem like this in terms of debugging? Should I just try to do everything at once and then see if it works and debug from there? Or should I do a more step-by-step procedure? In general, one of the most common mistakes of junior programmers, whether students or out in industry, just people who have less experience, is that they try to do too much stuff at once without testing things. And so the way that I would go about testing a program like this is I would open up one of these SQL commands, so like SQL queries like simple01.SQL like this, and see, okay, this command right here only is checking the tweets table. And so in order to know whether I got, in order to pass this test case right here, all I have to do is get the tweets table working correctly, and I don't have to care about, for example, the users table or whatever other tables there are. And so I'll start this by working on that tweets table, and that happens to be the second command down here. So work on this command right here, get that tweets table to work. Once you are passing this test case right here, that'll give you some reasonable confidence that the code here is working, and you can go on to the next table to insert things. I've divided up the SQL commands into what I'm calling the simple commands and the complex commands. The simple commands are all just things like select count star from some particular table, something very, again, simple to give you like just a really basic check, obvious check of like, is it conceivable that I have the right answer here for one of these problems? Just like the simplest thing you can do is count, do I have the right number of rows? The complex queries are doing more complex things involving joins and groups and where clauses. And so this is gonna be a more significant test of what your database is, whether it's correct or not. So I recommend thinking about the simple ones first and then thinking about the complex ones after that. It'll also probably be useful as you're working on this to think about your own tests that you might want to run. So like here, in order to do the tweets table, I'm going to go colon-tab E for a second. Let's open up my schema here, pg_normalized/schema.sql. In order to do the tweets table right here, we're going to see there is a foreign key right here, a foreign key in the tweets table to the users table. And so in order for the tweets table to be correct, I have to have the users table working before the tweets table. So in order for the tweets to work, I have to have the users table up here working first. The code happens to be structured that the very first part up here is inserting into the users table. And we saw that the first test case, though, was into the tweets table, not the users table. And so as you're completing this, as a stepping stone to completing this, there might not be like a specific test case to run, but you can just do some sanity checks of run your code, check to see like, did it actually insert things or not insert things? And so coming up with good like sanity checks that you're using as your own internal stepping stones on how to go like have some confidence that this is working before going on to this is an important part of this assignment as well. So hopefully that gives you a sense of how the answer of that question about how to go through debugging things and starting where to start. Any other big picture questions? Yes. Yeah, so the question is how to go about running those simple and complex files. And the answer is that you have your run tests.sh script right here. And so the overall structure of this repository is exactly the same as the Pagilla structure. It's just that the schema is different and the SQL queries are different. But you can still use your run tests.sh script right here to check that the queries are correct and match up with the expected. And the contents of this script file right here is exactly the same as what it used to be. It's a good question. Maybe one last thing that might be useful for you all as you're going through this project is that I've drawn a simple diagram up here of how all of the tables in the normalized version of the database, how they all relate to each other. So this might be a useful like image to be referencing as you're working through to decide, okay, I need to work on the tweets table next. What does that rely on? Oh, that relies on the users table over here, so I'll have to do that before the tweets. And then if you're moving on to say tweet media, what are the other tables that you'll need to fix before working on that one? Okay, I think that's a good stopping point for us for today. We're basically out of time. So if anybody has questions about this or the quiz or anything else, I'll stick around, get those answered. I have office hours today. And otherwise, I will, again, no lab tomorrow, so I won't see you tomorrow. I will see you next week.